Okay, so yeah, well, welcome back to the last day of the school. So for the second week, basically, most of the time we were doing enumerative geometry beyond numbers. So we consider categories, we consider cohomology. So today well, in my lecture, I hope to do some numbers eventually, do some explicit calculation for refined BPS invariants. So let me fix the notation. As before, we pick chi such that d chi is co-prime to 1. So it doesn't matter actually which chi you pick, because as we proved last time, the invariance or the decomposition theorem for the modular space we considered is independent of chi. So we have already proved the chi independence as a consequence of Ngo support theorem plus some other ingredients. So now we can pick any chi. For example, you can pick I to be 1, chi to be 1 if you like. And there I'm writing md to be md chi because nothing now is dependent on chi. And I'm using H to denote the morphism for the modular space of one-dimensional sheaves on P2. So this is a sheaf on one-dimensional sheaf on P2 as we considered last time, mapping to its support. And also, we learned from last time that the decomposition theorem for this map from MD to DH, so everything is completely determined by the smooth curves. So if we consider degree D smooth planar curves, so there is a universal one which maps to the Zariski open subset. I mean, just a complement of the discriminant. So this is the B, the total B minus the discriminant of the morphism. By the way, so for decomposition theorem in general, there is the discriminant certainly is the locus we care about, and there will be actually a sequence of locus which are generalizations of them, called the higher discriminants, and I think they will be discussed. They actually play a very important role in the decomposition theorem in general, and I think they probably will be discussed by Camila in the afternoon session. So it's not written in the website, but just let me announce it here. So the discriminant of H, the locus of singular fibers. Okay, so these are all smooth universal curves, smooth degree D curves. And the thing we proved the last time, which is our theorem A prime. So last time, okay, yesterday we proved that if you consider the decomposition theorem, the push forward of the constant sheaf, it is isomorphic to. So everything which showed up in the right-hand side are dependent only on the smooth curves. So you take R1, P, Q. So this is a local system calculating relative H1 for smooth curves. You take the wedge I, which calculates the HI of the corresponding Jacobian, and you do the intermediate extension to the entire base. You shift things correctly, and there is also a global shift, because of the perversity structures. So if we write R to be the relative dimension, which is, of course, D minus 1. This is the arithmetic genus of a degree D curve. So the sum is contributed from degrees I is equal to 0 to 2 times R, because everything is the intermediate extension of this local system, and this local system only lives in this degree. Okay, so yeah, so this is the formula we see yesterday, but then if we can take its global cohomology. Which tells us that the decomposition theorem can help us to decompose the total cohomology of the MD in terms of some pieces. So let me just write down this way. So bk, which is the Beatty number, calculating dimension of MD, and this can be written in terms of 2R plus 1 pieces. So this is, I just use the notation n I k minus I, where and everything's only dependent on the degree. So this goes from 0 to 2R. So this is, so every number here, this is the dimension, and k minus I is the dimension of the contribution of this wedge I summand. So the cohomology k minus I of the wedge I summand. Well, sorry, the notation is bad, but IC of wedge I summand. So in particular, this helps us to write one thing in terms of more things. So at the first glance, this makes our life more complicated, but actually it significantly simplifies the story, as I will explain. So these Nij, these are the so-called refined BPS invariants. Refined BPS invariants for the local P2, which is the total space of the P2 omega P2, O minus 3. This is local P2. Okay, so these are, well, this is the definition. So, so these are called refined BPS invariants, and in particular, they should encode, not, of course, if you sum them up in this way, they encode the information of the Beatty numbers, but actually, more interestingly, they conjectured, so all Gromov-Witten and the DT, Donaldson-Thomas invariants for the local P2 are conjectured to be rid of from these topological numbers. So this is, in physics, this is conjectured by Kuba-Kuma-Wafa, and mathematically by Honsono Saito, Takahashi, Kim Lee, and Maulik Toda. So these three, in the mathematical proposals, then every version corrected the previous version, but in this case, everything's smooth, so the three versions actually give you the same number. So which should be correct number? Okay, so the Gromov-Witten invariance for local P2 has been studied for decades, but it turned out actually these numbers behave better in some sense, which let me explain it, which is our theorem B prime. So theorem B, I stated last time, was the cohomological stabilization, but now this is the refined. The real stabilization actually happens for the refined BPS invariants. Refined BPS stabilization which is, well, it's proved actually in the same paper as I mentioned. So it tells us that the FNDIJ, this is equal to the coefficient of I is greater than 1, and this is 1 over 1 minus Q I plus 2 Tj Ti 1 minus Q I plus 2 Ti plus 2. Continue 1 minus Q I T I plus 2. Yeah. You expand this infinite series in the variables Q and T, and you pick the, depending on which invariant you want to consider, you want to go Nij, you just pick the Qi Tj. And this is correct on the nose if I plus j is small comparing to if the. Okay. So yeah, the I plus j here is actually the cohomological degree of the k here. So so in particular, this means that if you consider the small degree BPS cohomology, then all the refined invariants associated with it stabilizes into this product formula, and this bond actually is sharp. So if you go beyond this bond, then there are correction terms. And so if time permits, at the end I will say something about the correction terms probably. Yeah.
So in the formula, all the i's and the product come from the product, right? It's because you have two i's.
Yeah. So yes, it's the complaint of the notation. I put k here. Yes, IJ. Better?
Why did we move from P2 to local P2?
So all the definition is only about P2, but secretly these are the BPS invariants for local P2. So the reason is here is that if you for local for any Calabi-Yau, the BPS cohomology has been introduced by Yukinobu. You take the vanishing cycle and the vanishing cycle sheaf, and you consider the cohomology of it over the global modular space. And in the Del Petto case, this coincides with this classical invariance of the singular cohomology. There's nothing virtual there. So a warning is that, so in the first lecture, I said if you consider Beatty numbers of this MD they stabilize to the Beatty numbers of Hilbert schemes. But now we refine it. This is not the Hodge numbers of the Hilbert scheme of points on P2. So this is so the right hand side is in some sense a different refinement of the Goethe formula for Beatty numbers. But at first glance, this formula is strange, but I will make sense of it very quickly. How do you think about this geometrically? Okay, so let me draw a cartoon for these BPS invariants because I would like to view them, put them in the way as a diamond, like the Hodge diamond. Say 0, 1, say D, and 1, 0, D, and 0, 2, D, and 1, 1, D, and 2, 0, D. Okay, let me draw this cartoon to illustrate this phenomenon. We put all the refined BPS invariants in this like Hodge diamond. It's a diamond. So if you look at the Guba-Kuma-Vafa-Gomma-Witten correspondence, you see that in order to recover Gomma-Witten or DT, the thing you do is you forget about the homological grading, but you do alternating sum in this direction. So you consider the thing you consider is this one minus this one plus this one minus this one as a whole as a number, and then you do this for every line, put them together, and so you do alternating sum. In this direction, so you get this gives you Gomma-Witten DT invariance for the Calabi-Yau threefold. But if you even for the simple geometries local P2, the Gomma-Witten invariance can be calculated, but even in terms of modular forms, even if you consider genus 0, you see that actually the Gomma-Witten invariance does not stabilize. We will increase the curve class. So even the genus 0 Gomma-Witten invariance, they grow asymptotic, they grow exponentially. They do not stabilize. So the reason is that although every building block of diagram this every building block of this diagram stabilizes. So all the complexity comes from that you do the alternating sum here. However, so this theorem says if you do the summation in this direction, so these are the Beatty numbers of MD, and these are the stabilized ones. So in other words, these building blocks each building blocks actually behave better than the Common-Witten invariants. They stabilize when you increase the curve class, but when you do alternating sum, of course, then nothing stabilizes. So okay, so this is a phenomenon for local P2, and let me put a question here: is the refined BPS stabilization holds true for, say, local general type surfaces? This is actually the question Lucien asked the first time, first day, and you know, in Florence, there's actually a very famous trick for tourists, which is the 3-ball games. You know, you have 3 cups and you guess where is the ball. And actually, the situation is like that. I don't really have an answer. So, but if I want to bet, I would bet the answer is no. But that
one is a scam, if you know.
Yeah, but this is not. I'm honestly saying no. I don't know. I mean. Okay. So for any BPS cohomology, actually, you can ask this question. You have a curve BPS cohomology. It's about counting problem for curves, and you can increase the curve, increase the Mukai vector. Then you can ask whether the invariants are stabilized. And in the Dipartimento, yeah. So this is what I'm explaining for the Dipartimento case. That it's true, but if time permits, I will say some words about the Calabi-Yau situation. So interestingly, from the perspective of refined Kuba-Kumavafa invariants or BPS invariants, the Calabi-Yau case, the situation for the Calabi-Yau case is better and is much better understood, and in some sense, it's easier than the general the Fano case. So here we only have asymptotic formulas. In the Calabi-Yau case, there are closed formulas. Or at least conjecturally, there are closed formulas. So okay, so this is the main result and some analysis about it. So okay, one of the main themes for this school is that okay, we start with invariants, which are numbers, and we try to first lift it to cohomology with some representation on it, and then further to maybe categories. But for these invariants, I will do the same thing to explain that what's the cohomological lifting of the stabilization theorem. But I don't know how to do this categorically. So a cohomological lifting. So these numbers Nij, they are actually the associated gradient of an increasing filtration called a perverse Larrey filtration, so that the singular cohomology of D, it carries an increasing filtration which I have mentioned for a couple of times. I haven't defined it, which is the perverse filtration. People call this either perverse filtration or perverse Larrey filtration. So this is a cohomological shadow of the decomposition theorem. So the definition is the following. So if you view this cohomology of MD as the cohomology, the hypercohomology of the base, you push forward your Q. And this is a complex which admits the decomposition theorem, and you can do the perverse truncation functor here, which filtered your global modular space. So you have this object, and you can apply the truncation functor by considering the first k piece is contributed by the decomposition theorem, and this gives you an increasing filtration for the global cohomology. So in particular, we get a perverse filtration P0, P1. So this is an intrinsic structure associated with the singular cohomology of MD, and then this is more or less the definition that Nijd is nothing but it's just a refinement of the Beatty number using this filtration. So dimension of the GER associated graded, and the I remembers the perverse grading, and the J and I together remembers the cohomological grading. Okay. So yeah, this filtration, of course, by definition, is the cohomological lifting of these numbers. Okay, so this considers the left-hand side of the formula. Now what's the right-hand side? So let me write down another filtration given by some other structure of this modular space, which is the Chen filtration. So since the perverse filtration only remembers MD as an abstract variety which admits a fibration over some base, but the Chen filtration remembers MD as a modular space of sheaves. So you have MD, and it's a modular space over P2, so there is a universal family which I call capital F. Okay, so in order to define interesting cohomology classes, one can use the universal family to get correspondences. So I use the notation CKJ to denote. So the J is about which class you integrate over P2. So H, the hyperplan to the power of J. So the only interesting J is 0, 1, 2. You pull it back, intersecting with you take the cut product with 1 plus K of this universal family, and you make a normalization so that it does not depend on which universal family you choose, and you push forward. So in model of sheaves, this kind of invariants are studied a lot. For model vector bundles, these are the tautological classes, and in 3-calabi situation, these are so-called descendants, and the operators you consider. And this gives you, so every time you choose K and J, which tells you which Chen class you choose for the universal family, and then which class you integrate on P2, and you just combine them, this gives you a class on MD. These are the simplest classes one can construct, and some facts. So these facts actually rely on that MD is a modular space over the Pezzo surfaces. So the first is CKJ. If you consider all of them, they generate the total cohomology as a Q algebra, as a ring. Meaning that you take these classes and take all the possible products, they give you everything. And the second, which is actually guaranteed by theorem B, I explained last time. So which is the cohomological version, of the unrefined version for the stabilization. It tells us that no relations between these classes in 2D minus 4. You just count monomials, and then there's no room for relations because they generate. Okay, so now so we write down some simplest classes, and they generate everything, and so we can write down a filtration called Chen filtration, and they are just filtered by Chen gratings. So I define CK, the total cohomology of MD, to be the span of all monomials of the tautological classes where the only thing you bound, so these, when you choose different K and J, they lie in different cohomological grading, and the only thing you bound is the total Chen grading, which is only about which Chen class you take for the universal family. So you only bound this to be K, which is the same index here. So you can filter things. Since by the first fact, every class is tautological. So this Chen filtration, of course, exhausts the entire cohomology. So you have C0, C1, C2, and so on. OK, so these are two different structures. And so the next thing, let me introduce a theorem and a conjecture, and make some remarks. So let me start with the theorem. So the theorem B is the cohomological stabilization. Theorem B prime is the BPS stabilization, and now theorem B prime prime. This was conjectured by Waiter P, myself, and Kononov, and proved combining, essentially combining. So the first half was proved in work with Maulik, the one inclusion, Ying, and then it's completed in the PSSZ paper I mentioned earlier, which is that if you restrict your perverse filtration, which is the one associated with the morphism, in this range, this is calculating nothing but the Chen filtration. The same space. So in particular, the left-hand side is a cohomological lifting of the left-hand side of theorem B prime, because they are just associated dimension of associated graded. And on the right-hand side, because of the second fact, since there's no relation in this range, it's an exercise at the right-hand side. So it's an exercise that the right-hand side lifts the product formula, asymptotic product formula in theorem B prime. Because every class is a monomial of Chen classes. There are only three options. There's only three options of K, which is J, which is 0, 1, 2, and then you consider all Chen classes. There's no relation, so then if you count every Chen grading, it's a product. It's a coefficient of the same product formula I stated earlier. However, this is not the interesting part. The most interesting part. The most interesting part is the conjecture. So let me just. The proof combines. So the proof combines two things. Maybe let me say briefly. In MSY, we prove that one inclusion, the Chen filtration, is included in the perverse filtration for 2D minus 4. So using Fourier transform, And actually, the key player is the derived equivalence constructed by Arinkin, as mentioned in Yukinobu's talk, which realizes the duality by Fourier transform. And then later, so since one filtration is including the other, so then the secondly, it suffices to prove that the dimensions are the same, which was done in the PSSZ paper. So in other words, this is not, it's a cheating to say that this actually is a cohomological lifting because it uses the cohomological result. So you first prove a weaker one, which one infiltration is including the other, and you use, so this is actually theorem B prime. So we first prove theorem B prime and use it to conclude theorem B prime prime, not the other way. But the Chen monomial on the right-hand side provides some explanation how you refine the cohomology. And why, I mean, this is the geometric explanation of this product formula I stated earlier. Okay, let me make a conjecture which is due to, so we conjectured at the beginning for this range because, I'll explain the reason. But then Unan Lim, Moreira, and the P. So they conjecture that for P2, the two filtration are the same on the nodes without any cohomological constraint. For entire cohomology. And they verify this, so far the best evidence beyond the stable range. So they verify this for degree. So the hardest case is degree 5. So in this case, the MD is a 25 squared plus 1, which is 26-dimensional variety. And OK, so let me make some remarks about what's the subtlety of this conjecture. So the analogous statement. So if you replace P2 by the total cotangent bundle of T star C, the T star of a curve, and then the space, the MD will be just the Higgs modular space, and the morphism H will be the Hitching vibration, and then this P equals C statement is essentially equivalent to the P equals W conjecture for in the abelian Hodge theory. This analog statement for the Hitching system is equivalent to the P equals W conjecture, which is now proven independently in the joint work with Davesh and Hausel, Mallet, Minetz, Schiffman. And there's actually a third proof, which exactly is our motivation for establishing this Fourier transform after that. But actually, there is a key difference between the two geometries. One is the Hitching vibration, or more generally Calabi-Yau geometry, and the other is the final geometry. So there is a key difference. To me, this seems to be a subtlety. It's either a subtlety or the most interesting part. So let me share it. So a key difference. What time is it? OK. So either the perverse filtration or the weight filtration, which showed up in the Hitching system, or equivalently the Chen filtration for Hitching, for the Hitching space. So the statements, the conjectures are about filtrations, but actually these are, of course, now we know that they are equivalent. But this is actually a statement not for filtrations, but for decompositions. So for the Hitching space, have natural splittings. For example, so the tautological relation, so here Chen filtration is by definition they are given by, the filtration by the Chen grading, but actually Chen grading is a grading in the sense that tautological relations between the classes, tautological relations are homogeneous with respect to the Chen grading. In other words, every relations of the form like C2 gamma some gamma and C3 some gamma is equal to C5 some gamma. So if you count the Chen grading, it's always 5. So the relations for the Hitchin space, the relations generated by ideals like this. However, this is not the case for C. This is not the case for P2. In other words, the shape of the Chen filtration going beyond the stable range, because in the stable range, of course, stabilize the range 2D minus 4, there is no relations. So you don't have this issue. But now when the first relations start to show up, actually they are not homogeneous with respect to the Chen grading. So for example, it can happen something like C2I C3 J is equal to, this Chen grading has 5, but it's equal to so C2, and this is C5 of something. So if you have such relations, then okay, you can ask yourself, where's the exact location of this C5 in the filtration? By looking at this and the definition, you see, okay, this lies in the fifth piece. But it's not true because this is not optimal. By this relation, you further know that this lies in the fourth piece. So for example, this relation will tell you that the location of C5K, this class will be lying in the capital C4 in the Chen filtration. So in particular, the more and more relations you have, the more complicated the shape of the Chen filtration. And so in other words, if you want to prove this conjecture, it's an honest statement for two filtrations. You really have to prove that two filtrations are the same. So it seems to me very hard to split both filtration into a decomposition and prove they are true on the nodes. So yeah, this is one of the challenges. So then P equals C for P2. Is really a statement about filtrations, not decompositions. So let me say one word about why this matters, because if you want to prove two filtrations are the same, so usually there's one filtration is more concrete and the other is more abstract. So okay, the direct approach is that you first show that, for example, in this case, you can first try to place the Chen classes in the right location of the perverse filtration. If you manage to show this, then you get just one inclusion. But it's very hard to get the sharpness result that these two, if one filtration is including the other, you need some other ingredients to show that actually they are the same. So one of the very nice ways is if you have an algebra which splits, if you can construct some algebra or symmetry which you can get a decomposition which splits the filtration, then you can place the classes not only in the filtration, but correctly in the decomposition. I mean, the correct location of decomposition, so that you get this sharpness result. but it's not the case here. So at least I do not know how to like split either filtration. So now you probably really have to show that one is including the other and the other is included one. So it seems to be there are not many ways to show that two filtrations are the same. So it seems to be a challenging thing for me.
So you do not expect that the argument of Olivier and so on extends to this case?
Well, you should ask Olivier. But okay. So I think my understanding is that if you have their argument uses uses an algebra to split the perverse filtration, if I'm correct. And but these discussions suggest that there's no such splitting. Or if you want to split it, it has to be done in a tricky way. So I do not know, but probably Olivier has ideas of doing it. Yeah, but so you see, as I mentioned, that the filtration, the Chen filtration is really complicated when you go beyond the stable range. And even for degree 5, their calculation, many miracles happen which make the two filtrations true on the nodes. So yeah, so to me this is one of the challenges in this direction.
Is there also Chen filtration on singular moduli spaces? So you could have chosen D and chi not to be co-prime?
I chose d chi to be co-prime at the beginning.
No, but if you don't do that, do you still have a Chen filtration on null conjecture?
Yeah, a priori no, but probably there's something you can do with it. Yeah, you can view you can use the Chen filtration to be an operator on intersection cohomology or things like that. But I haven't thought about it. Yeah. Okay, so now let's turn to the proof in the last. Okay, so I have a little more than 16 minutes. 18, great. Let's prove the stabilization theorem. So, yeah, okay. Proof of the cohomological stabilization.
So this will be theorem B?
Yes. Even the BPS. So actually the BPS one is easier to be proven. So yeah, so even you care only about a cohomological state, but actually using the refinement is helpful, as you will see. Okay, so there are several steps. The step 1 is that we can throw out the worst fibers. So first we can reduce to integral curves. So here, remember that we consider B. So in the proof of the full support theorem or the chi independence, so the locus which played a key role is the locus of integral curves, which I denoted by B circle, B0. So this is the locus of degree D integral curves. By integral, I mean reduced and irreducible. And over which we have a universal curve. So I'm still using the same notation to denote this is the universal integral curve. Over B circle. And if you restrict your modular space MD to DH, so this is B, and you restrict it over B0, then the corresponding loci will be one of the compactified Jacobian fibration. So this is the compactified Jacobian parameterizing rank 1 torsion-free sheaves on these curves. So the good thing, so one of the upshot is that now if we are only interested, if we only want to care about smooth curves, this locus is too small because the boundary always have codimension 1. It's the discriminant. So, but the observation is that if we allow ourselves to consider not only the smooth curves but integral curves, then the boundary becomes much smaller, and this is an easy exercise which says that if you consider the boundary of integral curves, this is dependent on D. So in particular, this tells you that the codimension of the boundary of this compactified Jacobian is also equal to D minus 1. So this means that if we, by a excision sequence, if the cohomological grading is strictly smaller than twice of it, which is exactly 2D minus 4, we only care about the compactified Jacobian over B0. So the Nij D. So this will only be, you can just throw away all the fibers outside this JC bar by considering J B0 and IC B0 of wedge I. The same thing I wrote at the beginning. So, but of course, I wrote this, in order to define this, I wrote this equation for the entire B, but actually you can get rid of the boundary because this codimension thing. Okay, so this is the first reduction. We reduced for the entire B to the integral locus. So the second step is to, which also a standard in enumerative geometry, which is to using stable pair spaces, or more precisely relative Hilbert schemes, to study refined BPS invariants. So step 2, use relative Hilbert schemes. So most of the techniques I'm using here, actually, they are in literature for a while. So these ideas are not. So the ideas are there already. But the most surprising thing to me is that you just put all the things together. The bound actually, we get a sharp bound. The bound is really sharp if you do every step correctly. So the B0 here. So we have the compactified Jacobian of these sheaves, but on the other, so this is H. I still use H to denote it. But on the other side, we can consider a list of spaces associated with C, which are the relative Hilbert schemes. So I'm just indexed by some M. So these are relative C schemes, which are zero-dimensional, the pairs Z and CB. So where CB is a curve inside B0, so this is the integral curves. So these are integral curves. And the Z inside CB, this is a length M, zero-dimensional scheme. This is the Hilbert scheme of points on the curves. And of course, this morphism is nothing but sending ZB to just this curve. You just forget about the scheme and length M scheme and just remember the curve. Some facts. If CB is smooth, so over a smooth point, over a smooth curve here, the corresponding fiber is just symmetric product. So then the corresponding fiber is just the symmetric product of this curve, which is smooth, of dimension M. So But for non-smooth ones, if this is integral, this is no longer smooth, but this is irreducible. So there's only one component parameterizing the locus you like, and then there are boundaries. And the third thing is that, so the geometry of this Cm is relatively well understood if M is very large. So M is large enough comparing to the genus of the curves, then the Cm, you have an Apo-Jacobi map to the compatible Jacobian, sending this Z to the ideal sheaf of dZ, which is rank 1 torsion-free sheaf. And that this is a projective bundle. So in other words, now we trade these compatible Jacobians by Hilbert schemes, and when the number is very large, you don't get anything new. It's essentially just projective bundle over it. So the reason we still consider it is we are interested in considering the small m cases.
And over the entire B, what replaces the relative Bayesian scheme? It's a stable pairs. Over the entire B, is there something that replaces Cm?
Oh, you have entire B, yeah. Well, over entire B, you can consider the stable pairs in the sense of Panda Thomas. Yeah. Yeah, I will say some words about it. In particular, why things are easier in the stable range. And okay, so the key player is another support theorem. So I claim that actually all the formulas are deduced by just essentially one thing, which is a support theorem, but not for JC bar, which we have already treated last time, but for the Hilbert schemes. This is due to Maulik, Junliang, and also Shen. Using different approaches. So the statement is very simple, just support of this Hn. You can guess what it is? Everything. So sketch of the proof, depending on how much time I have, 7 minutes. Okay, I think that's enough. Okay, the sketch of a proof, just 2 steps. One, okay, so this is a statement which is uniform for M. No matter which M you care about, it's a full support. So the first proof, the first step of the proof is treated a case where M is large enough. In this case, it's simple because by this observation, it's a projective bundle over the compatible Jacobian. So this is H, and this is a projective bundle. And this is Hn. So here the proof. For the proof, I present the one given by Maulik and Junliang, and everyone is encouraged also to look at the Shen proof, which gives a lot of interesting ideas. Okay, so you consider when M is very large, this is a projective bundle, and this is a projective bundle, so you know that decomposition theorem for this step will not create any new support. So all the support is essentially encoded here. So in particular, support of Hn is the same as the support of H. And by Ngo support theorem last time, is everything. Then the second step is to perform a descending induction. So using a correspondence, so there is a very natural correspondence which you can connect the Hilbert scheme of M points with M minus 1 points. And you do the descending induction. And by analyzing the incidence of the correspondence, one can show that the support of HM, it actually, every support which showed up for the HM will actually show up for HM plus 1. So for this, you need to show, you need to control the geometry of the incidence correspondence, which shows that the smallness of some certain morphisms, which I omit details. But anyway, then combining these two ingredients, you get everything, because the two steps. The first is reduce everything, so reduce the statement to the compatible Jacobian, which was in Go support theorem, which we proved last time, and then this gives already the theorem for large M, and you perform a descending induction. Okay, so now finally let's explain that why this is enough. So at the beginning, I wrote the cohomology of JC bar, the compatible Jacobian, in terms of, so they are completely determined by local systems of the curves and smooth curves. But now, since we know that for the relative Hilbert scheme, it's also a full support. So in other words, if you consider the Beatty numbers for, so support theorem for HM tells you immediately that the BK CM can be expressed in terms of an IJD. Why? Because everything is determined by the local system given by the smooth curves. And you know the smooth curves, they are, so only the local system of the relative H1, this R1 P star of the smooth curve will contribute. And so if you write this down using the decomposition theorem by the full support property, you know that only these numbers will contribute, because they are just they are wedge I of the local system of the curves. Okay, so explicitly, but of course one can write down explicitly, which is some sort of McDonough formula. So the BK of CM, so this is, it can be written in terms of the leading term will be ND M. The same number of M, but the cohomological gradient is of course D minus M plus lower terms. By lower terms, I mean either lower M or lower total degree. So what this means? This means that if you are interested in NM something, the space you should look at is the relative Hilbert scheme of M points, where the M is matched with the perverse grading you consider here. Okay, so then the step 3 is finishing. So the step 3 is to finally use the Hilbert scheme of points. Now not for the curves, but for P2. So the observation is that if you consider the relative Hilbert schemes, so of course there is a natural evaluation map, because here this parameterizes Z, which are subschemes in CB. But you know CB are lying in P2 immediately, naturally. So the same number of points. So this is just a forgetful map. You forget about this CB and just remembering Z as a subscheme in P2. So the proposition is that, so the interesting parts are all the bounds, the estimate we do, but so here, but for the convenience and the time constraint, oh, I have 1 minute, let me finish it. So EV is almost, let me finish in one last sentence, almost a projective bundle over the Hilbert scheme. When M is small. Okay, so let me finish this in last sentence, and let me first explain what's the meaning of this. So this means that when K and M are small, so the kth Beatty number of this Cm, this is actually the same as the kth Beatty number of the Hilbert scheme of M points on P2 cross some projective bundle. And the bounds for K and M will be relying on the explicit analysis of this morphism, which I omit here. But here, the left-hand side will be talking to N D M something by the first observation. And the right-hand side will be talking to the Beatty number of the Hilbert scheme of M points on P2, and this is evaluated by the Goethe formula, which was actually explained in the in the lecture by Camilla on Tuesday. Okay, just put all the things together and check that all the bounds are matched. You get it. So in other words, last sentence. So here, in order to prove the cohomological stabilization, we first cut the entire cohomology into pieces. But this is actually helpful because when you do this, then for every piece Nij, we look at different spaces. So for every Nij, this is responsible by a different space, which is relative Hilbert scheme of I points, where I is the same number corresponding to the perverse grading here. So in other words, in order to treat the entire cohomology of MD, we actually have to use a list of Hilbert schemes. And so it's more natural even to consider just this refined PPS invariance comparing to the original Beatty numbers. Okay, so let me stop here, and thanks for your patience.